Okay, welcome to week 3 of Introduction to Robotics, and today we're going to be talking about robot geometry, which is still chapter 2 in the book. And so let's do a little review first, and then we'll get into the geometries. So we defined in week 1 that a robot is a piece of equipment that can be reprogrammed to perform multiple tasks. And it has 3 major components: the robotic arm or manipulator, the controller, and the power source. Okay. Uh, Most common robots nowadays have 6 axes. They're divided up into 2 groups. The positional axes, which are the first 3 axes starting at the robot base, and the orientation axes. Okay. The degrees of freedom, there are 3 linear degrees of freedom in the X, Y, and Z directions, and 3 rotational degrees for yaw, pitch, and roll. So W is for yaw, R is for pitch, or R is for roll, and P is for pitch here. Each joint of a robot arm has these 6 degrees of freedom: X, Y, Z, yaw, pitch, and roll. Okay. The tool center point is the point at where the work is to be done. So without a tool attached to the robot, we have the face plate, and the tool center point is the center of the face plate. But when we apply some type of end of arm tooling or end effector, we have to redefine the tool center point based on the device attached. The work envelope is the area that the arm of the robot can reach, so that it's basically the area that could be mapped out by the tool center point of the robot. The work cell includes the robot and the surrounding equipment to complete some given task. Alright, so now we're going to get into the various geometries of the robot. Okay. Now there's lots of different classifications that are done on robots, and so some of those are what we're going to talk about today is the arm geometry. Another is the power sources, which we kind of mentioned those before. We'll go into more detail into those. Applications, what application is this robot being used? And control techniques and path control. And we'll be discussing all these over the next few weeks. All right, so for arm geometry, we can basically have 4 different movements: Cartesian, cylindrical, spherical, and articulated. Okay. And which one of these that the robot falls into basically is related to those 3 axes, those positional axes. Are they a rotational type axis, or do they do just linear motion? Okay, and so we'll take a look at this here. All right, so the Cartesian system uses 3 linear degrees of freedom, X, Y, Z. So when we, in general, as people, we think about space, we think about a rectangular space having an X direction, a Y direction, and a Z direction. By default, the Z direction is usually indicated as up. Okay, but we can kind of redefine these if we want. We can kind of choose the directions that we point X, Y, or Z. But it's basically would map out a rectangle. Okay, so that's the Cartesian geometry. So when we look at this particular robot, you see that it has 3 linear axes. And so all 3 of those positional axes, 1, 2, and 3, are linear. And so this particular robot then has a rectangular work area. So it basically can reach any point in the box that's shown there. So you can put your end of arm tooling anywhere within this rectangular box. Okay. There are two types of Cartesian robots, gantry and traverse. Okay, the gantry system basically has all 4 points mounted, and so the box, the area, the work envelope that it can reach is inside of these 4 stands. The traverse system, on the other hand, is usually just mounted at one point, like on a pole, and so it can traverse through those. Okay. So again, the gantry has one axis supported, or all the axes are supported at the first axis is supported at both ends, such as like an overhead crane, where the traverse just has one point where it's mounted, and so all the axes are kind of stacked on top of one another. Okay. The pros of these types of systems, they create large rectangular work envelopes, so there's a large area, and everywhere within that rectangle can be reached by your end of arm tooling. It's very good for material handling, and they have a very rigid structure, and the payload is constant throughout the work envelope. So remember, we talked about payload on last week, and payload is how much it can lift. Since especially for a gantry type robot, since you've got supports on all 4 corners, you have a very solid and consistent payload throughout it. So that, what I mean by that, I mean that all robots have a max payload, but the difference is that if you're near that max payload with a articulated type robot and you're stretching way out, think of yourself as trying to stretch out, and you're trying to stretch out here and reach. The further you have to reach out and bend over, then the more stress that puts on your body, on your back, that kind of thing. With a gantry type system, since you've got that support on all 4 sides, it minimizes that stress even when working near that maximum payload. Okay, and another factor of these types of systems is that the positioning is pretty straightforward, because you're like, okay, I want to move in the X direction so much. You move that one axis and you've moved in the X axis. Where when we talk about the articulated, we've kind of seen those already. If we want to move in a straight line in the X direction, we actually have to move, probably all 6 axes are going to have to be adjusted constantly to move in a perfectly straight line. Alright, so some cons there. Usually these systems are increased height from what a articulated robot might be. They're more difficult to maintain, especially if it's a very tall one, that to get up there and maintain it, you're going to have to be up on a ladder or scaffolding or something, which is more difficult and to work on. And also the support structures may be blocking, they're obstacles that you'll have to work around when you're working within the cell or trying to move things around. Okay. Applications for these, material handling is one of the biggest applications. You can mount them over top of a conveyor line. They are also very good for inspection as items are moving down the conveyor line, and these are overhead of that, so they have a good view. Okay. So this is just kind of showing the Cartesian system here. We actually have an articulated robot in this case, and in this picture shown. All right. So, but again, the XYZ is you have a center point or an origin, and then you have your X, Y, and Z axis about that. And we did kind of discussed this last week too. The right hand rule is used for most of your standard coordinate systems, especially the world coordinate system. And that's kind of what this previous slide is showing here. For a FANUC style robot, you have axis 1 down here at the base and axis 2, and where those cross, that's where the origin for that Cartesian coordinate system is. Okay? And then you use the right hand rule to determine X, Y, and Z directions based on that origin point. After that, we can, the frame is a frame of reference. If you think about, say, a picture frame, you can pick that frame up and move it around, and the picture stays the same, but you see it from different angles as you move the frame. And so that's the case here when we're working with robots. We can set our frame of reference to match our needs. So depending on the type of robots, they have, of course, the world frame, which, as shown on the other slide, the origin of that is right where the two axes cross, and that frame is actually inaccessible. Like, you couldn't move your end of arm tooling to that point. It actually couldn't reach it with that particular robot. So you can actually redefine the frame from the world frame to a user frame, or with a tool frame. And we mentioned the tool frame last week also. The tool frame, remember, uses the left hand rule. And with FANUC robots, they also give you something called a jog frame, which is only used for jogging the robot and not for programming. But for standard programs, in at least FANUC robots, you always have both a user frame and a tool frame available and defined within the program. All right, our next two geometries here are the cylindrical robot and the spherical robot. Okay, so starting with the cylindrical robot, we see that the first axis is rotational. So axis 1 is rotational, it rotates around, but axes 2 and 3 are linear, and so they map out this cylinder or cylindrical type of work envelope. Okay, so again, this geometry is all about what kind of work envelope that you get. The next type is the spherical type. With the spherical type of robot, you have both axes 1 and 2 are rotational, but axis 3 is linear. And so this maps out more of a polar sort of shape. So you get rounding as it goes up and down, you get rounding on it. So that's cylindrical and spherical. Okay. There's a larger picture of that showing the work envelopes with a particular robot here, showing the shape as it reaches up and down. You can see the arch in that shape. Okay, so some of the advantages of these, they have usually have long horizontal reach, small footprint, again rigid structure. They can usually do quite heavy payloads, and they can do pretty precise positioning with a good controller. Okay, but they do have limited movement in the XY plane, so you can't really use one of these robots, either cylindrical or spherical. You can't get that end of arm tool to move in a straight line. Okay, it just won't do it. We could do it with our Cartesian, and when we get to articulated here in a moment, we can do it with that. But with the cylindrical or spherical, you can't get that end of arm tooling to move in a straight line. I mean, you can move it straight in and out along that third axis, um, but not when you're moving left and right in the X and the Y's, um, or, you know, in a couple of the directions, depending on how you define your frame. But you can't do that. But here's an example of where the cylindrical robot it could be used here. So we have some parts coming out of the die cast machine. The robot can swing around, and then it can reach straight out and into the die cast machine, pull the part out, put it in the quench tank, put it in the press, and then put it on the finished parts conveyor to send it further down the line. Okay, the fourth method then is the what they usually refer to as the articulated configuration. Okay, but it's also known as the revolute geometry system. So the revolute geometry system or an articulated robot are effectively the same. And here's a term for us today: anthropomorphic. Okay, this basically means human-like. All right, so out of the when we looked at the gantry type robot or the spherical type robot, they couldn't really make human type movements. They moved in linear ways or in spherical ways, but they couldn't do a very good job of mimicking the human arm or the human body movements. But the articulated do a much better job of that. They give you a lot more flexibility. And of course, there's two types of that: vertical and horizontal. All right, so we'll look here on the left. We have a vertical articulated robot, which is like what we have in the classroom. And you see this work envelope, the gray area, showing the work envelope is just, it's not smooth. It is smooth kind of on the outer edge, but on the inner edge, there's some points in there. So it's just not a real smooth. On the inside, you get points that you just can't quite reach. And one way to think about this is just think about yourself. If you wanted to reach back behind your back and scratch your back yourself or something like that, it's really hard to get your arm at certain points. Yeah, you can easily reach back and scratch at certain locations, but there's other locations which is virtually impossible for you to get your arm back there to reach. And so that's the same concept here with these articulated robots. There's certain areas where they just can't reach. Okay, where if we go back to the first one, the Cartesian type robots, the gantry and traverse, those everywhere within that that work envelope, that robot could reach. It could put that end of arm tooling anywhere within that large rectangular area. All right, but when we look at these revolute, think about revolutions. All three of your position axes are rotational with the vertical, and with the horizontal type, you have the first two are rotational, but the third one is actually a linear, and it's got a ball screw movement in it. Okay, so here's the vertical, and here is the horizontal. Now notice the horizontal units are known as SCARA units. And SCARA is an acronym standing for Selective Compliance Assembly Robot Arm. All right, and so they're used for very tight assembly things, like maybe putting chips on a circuit board, something like that, medical uses. Okay, so here is a vertically, this is the Fennec LR Mate, and it's a vertically articulated robot. This is a SCARA, or horizontally articulated um, Revolute robot. Okay. Advantages of these, they usually have a pretty long horizontal reach out. They have a small footprint, small size with a long reach. They can reach into enclosures and around obstacles much easier than, say, the spherical or even the gantry. This, they can reach in and kind of move around these obstacles more because they have 6 degrees of freedom, and they can do a lot of different sort of positions, just like you can with your hand and arm. Cons, because of the advanced control and stuff, they actually are much more expensive than the other ones that we looked at. The servo motor, the control system is got to be much more advanced for accuracy, so the cost drives up more. All right, so for this, you can just look in here at this work envelope, right? So this is a cylindrical type. We have linear, axis 1 and 2 are linear. Okay, this is a gantry type of robot. It's actually, in this case, only mounted at 2 points, and this is an articulated robot with a welding tool on the end of it, and there's a SCARA type robot. Okay. And just some various ones. Now here's a link to what's sometimes referred to as the spider robots. These actually have 6 joints on them and stuff, but they can actually move very, very quickly. Okay, and so these are some kind of pretty impressive little robots. Here, let's load this up. Okay, so here's just kind of a little picture of this robot moving pull balls around. And as you can see, it's moving quite quickly. Okay. And so those are really good for pick and place onto conveyor belts or onto circuit boards, like picking up small parts onto circuit boards or fan blades onto torque converters or things. Very, very fast, lightweight. They can't lift too much. Okay, but just to give you an example of a different type of robot that you may see out there. Fanuc makes them. They a lot of other manufacturers make them. They're pretty quick moving